Number 58. Compare the rate of the forward reaction to the rate of the reverse reaction when the system is at equilibrium. Oh my gosh, another freebie. Okay, if you're at equilibrium, what reason why we have a double arrow here is because the forward reaction goes as fast as the reverse. Again, so the rate of the forward equals the rate of the reverse at equilibrium. These are some things you just have to know, and that's what they're asking. I could care less about the blurb. Okay, so it's got nothing to do with that equation other than it's an example of a reaction equilibrium, which means the forward rate or speed is as fast as the reverse rate. That's what equilibrium is. The best example I can teach you is if I have a line with 3 people on one side of the room, and I have a line with 11 people on the other side of the room, and I ask the people on each line to switch places 1 person at a time per minute, okay, then what we're going to get is 1 person is going to go to this line as fast as 1 person goes to this line. So they're going to, 1 person's going to switch lines every minute. And so the rate of going to each line is the same, so we're at equilibrium, but something else pops up here. Even though they're not asking about it, I want you to understand the entire concept behind the question. The number of people stay the same. There's always going to be 11 people on this line, even though the people might change. That's why they call it dynamic. Dynamic is changing. And there'll always be 3 people on this line because they're changing positions equally, or the rate of changing is the same. So the rate of the forward equals the rate of reverse, and because of that, the amount of them stay constant. Now, the word constant's not part of this question, but it will be in others. So be aware that equilibrium, rate of the forward, equals the rate of the reverse. Always, I've seen this in multiple choice questions. It's the same kind of question. Because of it, the amount of reactants and products stay constant. Onto the booklet. It said here the rate of the forward reaction equals the rate of the reverse reaction equals is the key thing here. I could have just said equals. I mean, they give you all this space here. But don't feel like oh my God, they're giving you all these lines. These answers have to be long and winded. No, don't do that. Get to the point and get out. So there you go. On to number 59. Number 59. State how the equilibrium shifts. So this is the Chatelier's problem, where we want to shift out of equilibrium when the pressure of the system is increased at constant temperature. Okay, so we get a reaction at equilibrium. The forward reaction goes as fast as the reverse. When we say a shift, what we're going to say is one of the directions, either the forward or the reverse, now is going to get faster than the other. Remember, at equilibrium, the speed of the forward or the rate of the forward equals the rate of the reverse. So they're both going at the same speed, and the amount of the reactants and products stay constant. But if I can cause a shift, which direction? The shift represents one of the directions going now faster, which means you're going to lose, okay, the things you're shifting away from and increase the ones you're shifting toward. Okay, so there's a stress and then there's a response. So the way that I teach this is that if you give yourself a little chart, we have a stress and a response. The stress is that the pressure is increased. Now the reaction wants to shift to regain its balance. Things in nature always work toward equilibrium. Equilibrium is a low energy state. Okay, so therefore the pressure has gone to what? You're going to push it out of equilibrium, and then it's going to want to lower the pressure to regain its balance. So the response, okay, the response is always going to be in the reverse of the stress. Stress is what people do. The response is what the reaction does. And the reaction is going to shift either left or right, go faster toward the left or go faster to the right to regain the balance. If you have no idea how to do this, you're either going to say shift left or shift right. It's a 50-50. Anytime the pressure is a stress, you count moles of gas. Okay, so in my problem here, On the reactant side, I can see there's 2 moles of gas. On the product side, I see there's 1 mole of gas. So if the reaction wants to lower the pressure, doesn't it make sense it's going to shift to the side with less moles of gas? Of course it does, because particles of gas collide. They create the pressure. So this means that this reaction is going to respond by going faster in the forward direction to lower the total number of gas particles and then subsequently the pressure. So we would say shift to the right. All right, to the booklet. It shifts to the right, okay? Or it shifts to the side with a few moles of gas. Or it's going to favor the forward. Favoring the forward means the forward's now going faster. Okay, shifting to the right means that we are now going faster in the forward direction. Okay, all right, so a little Chatelier's problem there. On to number 60. Okay, number 60. Compare the entropy of a sample of dinitrogen tetraoxide gas at 25 and 1 atmosphere to the entropy of the same compound, or I should say, sorry, the same compound but at a liquid at 15 degrees Celsius. So what we're really doing with all these words is we're comparing the entropy of a gas to the entropy of a liquid. Now, of course, what is entropy? Entropy is the measure of randomness. It really is a measure of how energy disperses outward, but you can think of it as the spreading out of energy. Things in nature spread out. When they're together, there's more potential in terms of, I'll just say that things spread out naturally in nature. Leaves on a tree break down into smaller and smaller pieces. It's how the universe works. Our universe is expanding. So when you think of entropy, think of the spreading out of energy. And the way that particles can do that is when they become individual free particles, they can move independently. Solids have lower entropy because solids exist in a three-dimensional structure called a crystal lattice. Here's one example. Sometimes you have to draw. It's a regular repeating geometric structure. And the next what? Particle or atom has to be in the next spot of the crystal. And because these guys can't move independently, all they can do is wiggle in their fixed positions. They don't have a lot of randomness. There's a lot of order here, a lot of structure. Okay, now when they become a liquid, they're free of the crystalline structure, but they still have a lot of attractive forces. Liquids have to basically stay in their container. And then of course when they become a gas, they have the greatest molecular motion or degrees of freedom, and therefore they spread out a lot more than a liquid can or a solid can. And their ability to spread outward and have their energy dispersed, okay, or they have a lot more random motion, is going to occur for a gas. So the entropy for a gas, okay, is going to be greater than a liquid. And interesting enough, they gave you different temperatures. If this was still a liquid and the liquid was increased to 25 from 15, the entropy would also increase. If you add energy to a system, they're going to move more. And if they move more, they're going to spread out more. We know that the density of a liquid decreases as it gets warmer. Okay? Right? And the density of a gas decreases as it gets warmer. That's how hot air balloons work, right? So that's the same idea. The ability to spread out, be independent, be more random is how the universe wants to work. Energy that's, stored in a small area wants to be free, okay? And we know that gases have greater molecular motion. So in any case, you would say that the gas, of course, has greater randomness than the liquid. the entropy is greater in the gas. And certainly you can phrase this so many different ways. The entropy of the dinitrogen tetraoxide in the gaseous phase is higher than the liquid dinitrogen tetraoxide. If you want to work, use all those words, but you don't have to. The entropy at 15 degrees Celsius, you can just talk about temperature, right? Forget about the phase, is less than that of 25. As things get colder, they move less. They're less degrees of freedom. They don't spread out as much. Okay, so many ways to say that, but the gas, of course, spreads out. It's more random than the liquid. On to number 61. Number 61. Going right to the question. State the change in oxidation state of copper in this reaction. Okay, party people, we've got to know that the copper is a standalone element. If it's standing alone or just bonded to itself, you've got to know it's an atom, right? And I say atom, you should say neutral. Atom, come on, say neutral. Atom, neutral. Atoms are neutral because their protons equal their electrons. So standalones are zero. They have no charge because their protons equal the electrons. All elements or atoms in the periodic table are written as atoms. So the atomic number is equal to the electron number. Now, when it bonds to something, it changes. Okay, so what is copper? Okay, so we know it's going from copper 0, but what is it changing to? Now, once it's bonded to something, it can't be a 0 because now it went under a redox reaction. It's going to lose electrons. Standalone metals can only oxidize, but in any case, it's not really what this question is about. What the question is about is what is the charge on the copper here? So this is an ionic compound. Has to equal 0, but the components have charges. So what's the charge of nitrate? Notice there's 2 of them. If you don't know it's -1, okay, there's a place to look. Let's look. So table E, I call what the heck is that table? These are the clusters of mostly non-metals that bond covalently and have a charge. And therefore they can make ionic compounds. That's why some questions you'll see which compounds have both ionic and covalent. You look for a polyatomic ion. But in this question, we're here because we want to know what the charge of the nitrate ion is. The nitrate ion is negative or -1. So the nitrate ion, not the nitrate ion. Nitrate ion, not the nitrite ion. I can do this. Okay, so any case, this ion right here, the nitrate ion we're after, is -1. Okay, and that's really important because there was 2 of them bonded to copper. So that means the collective charge of all the nitrates is -2. Since there's 1 copper, copper is +2. But let's look back on that if you don't remember. So because each nitrate's -1 and there's 2 of them, that means the overall charge due to all the nitrates is -2. Remember, the whole thing has to equal 0. Ionic compounds equal 0. Since there's only 1 copper, the copper must be +2. So what are they looking for? They're looking for the change in oxidation state. So I would say it goes from 0 to +2. Okay, let's get to the booklet. So from 0 to +2, and notice the booklet really helps you define how to answer it because we weren't sure what to say there. You can also say from copper to copper +2. You could do that as well. Okay, or from 0, you can write the words out if you want. Okay, so again, 0 to +2, pretty straightforward. Okay, number 62. Number 62. Based on table J, they're telling you to go to table J. State why copper reacts spontaneously with silver plus. I'm having a tough time speaking this afternoon. So why does copper react with Ag plus? Now, it's important you understand what this is because it can get a bit confusing even though I have trouble speaking today. So copper in a redox reaction, because this is what this is, oxidation numbers are changing, can react with Ag plus. Now, think with me for a second what this is about. Standalone metals can only oxidize. So when you see a reaction like this, okay, any metal hanging out by itself is oxidizing only. Copper cannot gain electrons and become negatively charged. Copper plus 2 can. That's different. But all metals written by themselves, like magnesium, gold, silver, they're zero, and they only become positive by losing their negatives or oxidizing. So I know that the copper must oxidize if this is going to work. The one who has a charge, in this case, the silver plus, has got to reduce. So the way that they wrote this reaction, they said the word spontaneous. Now what that means is that it's going to react without any input of energy. And it only works if the one who is oxidizing is strong enough to force its electrons on the one who's reducing. Okay, so we have to recognize that Ag plus can only get reduced. And how do I know that? Because Ag plus, okay, is not a standalone metal. It's not hanging out by itself. It can gain an electron, which it will in this process if it works. We have to find out if it does, and it will become Ag0. It's going to gain one electron. Okay, copper, if it gives one electron up, is going to become copper plus 1. So this would be the net ion equation if one electron was being passed around and if it was spontaneous, if this can work. You've got to see that. So the one losing has to be the one who is oxidizing. But again, to pick out who is oxidizing, find your standalone metal in the reactant side. Now, to know if this works, we go to table J, and there's a list of metals. The metals who are best at oxidizing are on top. So comparing copper with silver, you're just seeing if copper is higher than silver in table J. And if it is, that means copper can oxidize better than silver, so it can push its electrons onto the silver plus, and this will work without an input of energy. Okay, so let's go to table J. Well, there it is, and there's our list, okay, of metals. The most active are the ones that react the best. Metals that stand alone are active by losing electrons. Metals lose electrons. Guess what nonmetals do? They gain. So the list over here is who's best at gaining. Ger means reduction. So this is a list of who oxidizes the best. So if copper is going to oxidize without an input of energy, that's what spontaneous means, it's got to be higher than silver. And so is it higher than silver? Yes, it is. So when you put copper next to silver ions, the one highest, if it's higher, will spontaneously react with the metal who's going to be an ion that reduces. The higher one always oxidizes. So since copper is higher than silver, it will oxidize spontaneously. So based on table J, why does copper react spontaneously? It's just higher on table J than silver. That's all you need to do here. Copper is located higher in table J than silver. Okay, you could say silver is less active than copper. Copper is more active. Okay, that's all there is to it. On to number 63. Number 63. Write a balanced half reaction equation to represent the reduction of the silver ion. So Leo the lion says Ger, so gaining electrons is reduction. You can also do oil rig, right? Oxidation is losing, and then reduction is gaining. I don't care what you do, but since we're talking about reduction, we know that we're going to be gaining electrons, and we got the silver ions. And they told us what the silver ions are. They're Ag, well, they're Ag plus. Okay, they're right there. And they tell you that in this equation too. Nitrate's -1, so silver is +1. So what's the half reaction? We're going to start with our silver plus. That's the reactant. We're not changing sides. So the silver plus comes from that side, right? That's +1. That's +1 because we learned that in table E, nitrates are -1. So we really have Ag plus there. Now, it's going to become what? Well, it's going to become a silver, a standalone silver. Okay, so I write Ag and I put a 0 here. How does that happen? How does a +1 become a 0? Remember, both sides have to have the same charge. Well, again, they said reduction, gaining electrons, or reduction is gaining. I don't care. I need an electron right here. Okay, +1 E negative. And the way that works is both sides of a half reaction have to have the same charge. By putting the 1 electron there, plus 1 is 0 is a difference of 1. This is a 0, and this is already a 0. That's perfect. If you put the electron on this side, that'd be incorrect. A -1 and a 0 is -1. This side's plus 1. So again, where you put the electron is important, but reduction is a form. Okay, reduction is a form of gaining electrons. Okay, and so you should know gaining something like gaining energy, it's like endothermic electrons on the reactant side. Okay, so that's what we put in our answer book. 53, there's my ion, and there's me gaining an electron here and making a silver. Now, they could accept a couple of different things. If you notice, there was actually 2 silver ions in their reaction, so you could put 2 electrons here, and this would make a 2 here across the board because of conservation and mass. So that could be accepted too. I say keep it simple. For every 1 silver plus and 1 electron you make, 1 silver 0. Okay, so bottom line is we're gaining electrons. Electrons are on the reactant side. Both sides of the half reaction equals 0. Okay, so make sure you've got that down. It's a great little check here, but that's a reduction, a correctly balanced reduction reaction. The charge on one side is the same as the charge in the other, and there is 1 silver on one side, and there's still 1 silver. So mass and charge, okay, are both still conserved there. So on to 64. Number 64. So again, we have this blurb, and I'm going to go right to the question. Write the name of the laboratory procedure used in this activity. Guess what? Gotta go read the blurb in this case. So during this laboratory activity, we have a certain amount of acid is exactly neutralized by a certain amount of base. This should scream to you a certain procedure. Every single, I would say, Regents students should have done a procedure where you took a burette, which is an emptying device, and normally you'd fill it with the base, but it could be done the other way. And you would add it to an acid like HCl, and you would figure out the concentration, or you would figure out something about each other by dropping base onto acid until all of the acid has been neutralized. And we use a chemical indicator to help us get an approximate spot where we stop adding the base to the acid. And using a certain formula, we can actually solve for the molarity or the amount of acid or base needed to neutralize. This is called a titration, okay? And we use acid-base titrations in Regents chemistry, but you can also do gravimetric titrations or redox, volumetric redox titrations, where you're matching the moles of one compound with the moles of another compound it reacts with. In the case of acid and base, the key is neutralized. You hear the word neutralized, and you see, I always say if you see 3, okay, variables, okay, in this case, the milliliters of the acid, the milliliters and molarity of the base, okay, this screams to you acid-base titration. So the word titration just really means that you're using one chemical's information to answer another in a laboratory procedure. So knowing how much, okay, sodium hydroxide I'm adding, I can figure out exactly how much acid I have, because generally speaking, the acid, okay, in this case the H plus or H3O plus equals the equals the hydroxide for the base when it's neutralized. And the word neutralized means we take away the danger of each of these ions. In high concentration, H plus is very dangerous because it can break down, react with metals, it could break down flesh. And the same thing with hydroxides. They're just as dangerous in high concentrations. High concentrations of hydroxides can break down organic material and metals as well. And they're dangerous at high pHs. And of course, having a lot of H pluses or H3O pluses are also dangerous at very low pHs. But if you add a base, the right amount or the exact amount of hydroxides to this dangerous H plus, you can neutralize both because they're going to become just water. And water isn't dangerous. Okay? So that's what neutralization is. So any case, we're talking about a titration, okay, an acid-base titration. Titration is the word, and I've seen this answer in this type of question given in a multiple choice section. So going over the multiple choice, you're not inhibiting or hurting your studying for the part 2. It's the same type of questions, just kind of hidden. They accept a volumetric analysis too, but they do not accept neutralization because I believe that's just kind of repeating the word neutralized. Okay, so 64 is titration. On to 65. So number 65, show the numerical setup. Another question where they just want you to put the numbers in. Therefore, you need a formula for calculating the molarity of the HCl solution. Very classic Regents question. It's on every Regents, whether it's on the multiple choice section or in the free response, and here we are. So we want to calculate the molarity. We want the concentration. Molarity is big M. We want to know the molarity, and oftentimes that's the reason why we do a titration. You can see where I've highlighted, those are the values given. There's 3 of them, and there's a big M involved. And we learned from 64 that this is a titration experiment where we're neutralizing. The key words are neutralized, acid and base. You see big M. There's 3 variables. So we need an equation with 4 things. So let's go to table T to remind ourselves in this 3-hour test where I can look if I forget to jog my memory. Here we are in table T, and looky here, we've got a titration formula. If you don't get that, look at this, the molarity of the H plus. There's the word acid, there's the base, all these keys to help you remember that this is the formula we use to figure out the other chemical, in this case the acid or base, given information about the acid or base given. So MV of the acid equals MV of the base is what we use here. This happens every test. See more questions. You'll see more of these questions. You'll see more test questions or see more total tests and do them. You'll see this particular question popping up at least once every test. So let's get these values in and get this answer done. I need the titration formula for this titration procedure, acid and base. Let's plug in our values now. Okay, so they gave me 15 milliliters of hydrochloric acid, so that's my 15 milliliters, that's my volume. We don't know its concentration. They're calculating the molarity of the acid, so that's my unknown. If you want to keep that, you want to use an X, that's fine. And then what's the molarity of the base? Hey, they gave us 0.11, and they gave us 18.2 milliliters. My friends in chemistry, that's all there is to it. I'm just going to plug that in. In fact, they're not looking for an answer. They just want a setup. You could solve for it. It wouldn't be wrong. Let's put it into the booklet of fun. There it is. M of A, V of A equals M of B, V of B. MV of the acid equals MV of the base. We're just plugging into what they just gave us. Okay, understanding what a molarity is and what a volume is, and we're solving for the unknown, except we're not solving, we're just plugging in because they just want the setup. So what I have here is perfect. Okay, certainly you could start solving for this and put this under 15 if you wanted to, but again, the way you just plugged it in and left the unknown as it is perfectly fine. No reason to get that wrong. These questions should be getting similar. And if it's the first time you've seen this, you need to do more tests, okay, to see this titration volumetric problem. Common, one of the most common math questions on the Regents. On to number 66. Number